So first example of an optimization problem. A box with a square base and an open top must have a volume of 32,000 cubic centimeters. Find the dimensions that will minimize the amount of material used. So first thing I want to do is draw a picture of the situation. So a box, sort of force a three-dimensional perspective on this one, with a square base and an open top. That'll indicate that the top is open. That'll continue down there, that'll continue over there, and this will continue over here. So a square base and an open top is supposed to have a volume of 32,000 cubic centimeters. Find the dimensions that minimize the material used. So with that in mind, first thing we do is identify what did we use in this setup for the problem that indicates optimization, and we got it right there. Minimize the material used. So with that in mind, we need to define several variables. So here are some things that we could define. We were told the volume of the box. We'll use V for volume of the box. Now, for a box, in order to determine a volume, you would need a length, a width, and a height for this. However, we were told that it has a square base, and because it's a square base, the length and the width will be equal to each other. I'm going to define that variable to be x. This will be the length and width of the box. So we'll throw an x here and an x here to indicate that that's the length and the width of the box. We'll also need the height of the box. The height of the box we'll define to be the h variable, so height of box. We'll toss that right there so that we know that that's the height of the box. Now, what are we actually asked to optimize in this? We're trying to minimize the amount of material used to create this box. Now, with that in mind, the materials that would be used to create this box would be that square base that we have here, as well as the 4 side walls. Those are all rectangles and squares, which means that in order to minimize the amount of material used, we need to minimize the surface area of the box. We'll define S to be the surface area of the box. So with those things in mind, we are trying to optimize S. That makes S our objective variable. So our goal is to try to get S in terms of only one variable. However, we're going to start by defining it in terms of 2 variables. So the total area that is going to create this box is going to be the square base plus the rectangular side walls. Now the good news is, because we have a square base, all 4 of the side walls, the front, the back, and the 2 sides, are all going to be the same area. There are 4 of them. Now, the area of the square base is simply going to be x times x, or x squared. And then we'll have 4 side walls that all have a base of x and a height of h. We'll call that 4 times x times h. So that is our surface area in terms of 2 variables. Now, we need to relate these variables in such a way where we can make a substitution on this as well. That's where the volume is going to come in. The volume of a box is supposed to be the length times the width times the height. In this case, that would be x times h, or more simply, x squared times h. But we were told what the volume of the box is. The volume of the box is 32,000 cubic centimeters. So 32,000 is going to be equal to x squared times h. Now, we were supposed to, according to our directions or our strategy for the problem, perform substitutions to get the objective variable in terms of only one variable. So your options are, you can either solve this for x, I'm shaking my head right now, or you can solve this for h, I'm nodding my head right now. So which one do you want to solve for? Yeah, I agree. Let's go ahead and solve for h. If we solve this for h, we can avoid having to use any nasty little square roots or things like that. So we solve for h, we get h is equal to 32,000 divided by x squared. That is the substitution that I am going to make to get our surface area in terms of only one variable. So I'm going to pull this surface area formula down here, and we'll make a substitution on h. So this will be x squared plus 4 times x times the artist formerly known as h. Perform this substitution, we get 32,000 divided by x squared. Now we have the surface area in terms of only one variable. I am going to perform a little bit of algebra to try to simplify this expression, but this is the thing that we are going to optimize. So x squared plus, we can treat this 4x as though it's 4x over 1, cancel out one factor of x, and multiply the 4 times 32,000. 4 times 32,000 is going to be 128,000 all over x. Now, if suitable, try to figure out an appropriate domain for this. And really, I think the only thing that we need to point out for the domain is that x was referring to a length. Lengths cannot be negative. We also see that the length can't be 0, otherwise the volume would be impossible to figure out. So really the only domain that we have for x is that it has to be greater than 0. We can maximize the amount of surface area used by essentially allowing x to get really, really close to 0. Yeah, we don't want to do that. That sounds like a terrible idea. So instead what we're going to do is take this s equals x squared plus 128,000 times x, and we're going to take the derivative of that. Now before I take the derivative of this, I am going to do one more step of algebra to make this derivative a little bit easier. We'll call this x squared plus 128,000 times x to the negative 1 power. I'm going to recopy that on the back of this sheet so that we can continue to optimize. So that'll be s is equal to, once again, x squared plus 128,000 x to the negative 1. I'm going to differentiate this. The derivative is going to be ds over dx. Derivative of x squared will be 2x plus 128,000. That's a constant multiple, so we could ignore it for the time being. And that'll be negative 1 times x raised to the negative 2 power. In order to figure out our critical values, we'll need to set this equal to 0. We've already defined x to be greater than 0, so we don't need to worry about the fact that there's a domain issue at x equals 0. Recopying this, using a little bit of algebra, we arrive at the following. This will be 2x minus 128,000 divided by x squared is equal to 0. I'm going to start taking algebraic steps to solve this equation. First thing I'm going to do, multiply both sides by x squared to clear out our fraction. This will give us 2x cubed minus 128,000 is equal to 0. I want to isolate x on one side, so I'm going to add 128,000 to both sides. Divide both sides by 2. And finally take the cube root of both sides. So x will be equal to the cube root of 64,000. If at this point you want to toss that into a calculator, that's probably a good idea, but I can tell you right now that that is 40. Now, that takes care of x, but the original problem said determine the dimensions, so we're going to need to figure out the height as well. Borrowing from earlier, we said that the height is going to be equal to 32,000 divided by x squared. I'm going to plug in the value of x that we just calculated. That is 32,000 divided by 40 squared. Once again, if you want to take that to a calculator, you're welcome to do so. That is going to be equal to 20. We now have values for all of our variables except for the surface area. Now, technically, we were not asked what the surface area is, but it is still something that you could calculate as part of the process. So, to interpret all of what we just did, that would be to minimize the amount of materials used we are going to construct a box with a base of 40 centimeters by 40 centimeters and a height of 20 centimeters. After you do that, you can calculate what the minimum surface area is by saying S is equal to, it was x squared plus 4xh. That would be 40 squared plus 4 times 40 times 20. And according to my calculator, aka brain, that would be 4,800 square centimeters, keeping in mind that that was an area that we just calculated.